Hello and welcome back to Nunley Math. Thank you so much for taking the time to watch these videos. I'm very excited to be back with you. This is the second lesson and the third video in our series on equation solving, primarily geared toward Algebra 1 students and Algebra 1 teachers who are interested in seeing some new and different ways of approaching things. I hope you enjoy what's going on here. I'm going to keep this as concise as I can. Thank you especially to my students who are providing feedback to me as I make these, giving me advice on how to make them more user-friendly and helpful. I hope to take those pieces of advice into consideration here in the near future. Very excited to see what we can do here on YouTube. So without further ado, let's get started. The last time we spoke, or the last time we had this video, we talked about the fact that all of algebra is based on the idea that there are certain patterns that exist in numbers, and these patterns are regular, predictable, and unchanging. Now, we talked about several of these patterns, typically refer to them as properties, and we went through kind of where they come from and how they're useful. And spoke a little bit about their application in equation solving. Now, in my classroom, I provide my students on the first day of school with a list of algebraic properties. Notice that they are grouped by things that are similar. The center has a little more formal of an algebra definition, and on the far right we have kind of a general English definition. I find that my students understand the concept a lot better if we talk about it in very plain language and then go back to the algebraic representation rather than just throwing up algebraic representations onto the board. Now, once we did that, we talked about how we can solve single-step equations using these algebraic principles. And we talked about very simple equations. For example, x minus 11 equals negative 14. And I do realize this is actually the first example I'm showing you, but this is actually a screenshot from the previous slideshow. If I wanted to solve x minus 11 equals negative 14, or find the solution is the value I can plug in for x that would make this sentence true. And we said the way that we can find this is by taking this minus 11 and adding a positive 11 to it. We pick the positive 11 because negative 11 and positive 11 are additive inverses. Additive inverses are things that add together to make a 0. So we choose that positive 11. We do it on both sides of the equation because the property of equality says that whatever we do to one side of the equation, we also have to do to the other. When we do that, we get x plus 0 equals negative 3. And of course, adding 0 doesn't do anything. That is the additive identity. So we can write that as just x equals 3. So we know that if we put negative 3 into this equation, that it should work out. So we double check that by saying x minus 11 equals negative 14. Since we said negative 3 should make it true, we plug that in. Negative 3 minus 11 equals negative 14. And negative 3 minus 11 does indeed equal negative 14. So the two sides match. Once I know both sides match, I put a check mark confirming that my solution is correct. We then took a multiplication example. We said if we have negative 4 times x equals negative 9, and we want to find what value makes that true, we have to get rid of this negative 4. The easiest way to get rid of that negative 4 if it is multiplied by x is to do the inverse operation, which is dividing by negative 4, or multiplying by the multiplicative inverse, which is negative 1/4. Remember, dividing by negative 4 and multiplying by negative 1/4 are essentially the same thing. In either case, when I do that, I end up with a 1 here on the left-hand side. Notice that the property of equality says I can do whatever I want as long as I do it on both sides. So I've done it on both sides. Negative 9 divided by negative 4 is 9/4. I spend a little bit of time in my classroom talking about the fact that we really want to get comfortable with this notion of fractions instead of decimals. We also want to get comfortable with the notion that fraction is really just a division problem. And this is a great way to illustrate that. I ask my students 9 divided by 4 equals what? When I tell them it's 9/4 at first, they laugh and then they get very, very excited because that seems fairly easy to compute. Certainly you can turn that to a mixed number, and there are a lot of cases where we like it to be a mixed number, but for our purposes today, we'll go ahead and leave it improper. To do the check again, we rewrite the original problem, we plug in 9/4, And we know that negative 4 times 9/4 is negative 9, so it does check out. By the way, this is a lot of the reason I like to leave these improper is when I do my checks, most of the time you're going to have to convert the mixed numbers back into improper fractions anyway in order to do the check, and it seems easier not to mess with that. And then we did a couple examples where we had fractions multiplied by our x. Notice you have your unknown here. It has been multiplied by negative 5/8. If I want to eliminate that negative 5/8, my best bet is to try and find the multiplicative inverse so that I can turn it into a 1. The multiplicative inverse of negative 5/8 is negative 8/5. I multiply those together and that becomes 40/40, which is a 1. The property of equality says whatever I do on one side, I have to do the other, so I also do it over here. 25 is the same as 25 over 1, multiplied by negative 8/5 is negative 200 over 5, which becomes negative 40. Now, I certainly do realize there are some shorter ways to multiply two fractions together involving cross-simplifying, but that's not the focus of the video here today, and it seemed much less confusing just to go ahead and do it the longhand way. Once again, we rewrite the original problem, substitute in the value we said should work, and then simplify our final solution in order to verify that we're right, and we give it a check mark. This slide I've actually prepared just for you to give you some practice solving the problems. I know a lot of times the tendency in a YouTube video is just to explain to you how to do it and let you see the examples, but I thought it might be worthwhile to give you an opportunity to pause the video and try these on your own. My suggestion to you is that you take the time to pause this, do practice 1, play the video, see if you did it correctly, pause, do practice 2, once you finish, check your answer with the video, and so on and so forth. It is much more instructive and useful to you to do the practice on your own so you can see the errors you tend to make than it is for you to just watch the video and see me tell you how to do it. If I tell you how to do it, you're going to get it right every single time. Now, I am operating under the assumption that you are pausing the video, so I am going to go ahead and talk. I will do these very, very quickly because I think you can see the results just as well as I can talk about them. So I'm going to do this with quite a bit of speed. I have x divided by 7 equals negative 6. In order to get rid of divided by 7, I have to realize that divided by 7 is the same as times 1/7. I'm going to use the multiplicative inverse of that 1/7, which is 7 over 1, and do it on both sides. I multiply that together, I get 7x over 7 equals negative 6 over 1 times 7 over 1, which gives me 1x equals negative 42. The multiplicative identity says that multiplying by 1 doesn't do anything, so my solution here is x equals negative 42. Here's the check. If you want to spend some time looking at that, you may. Practice number 2 is actually a little bit easier than practice number 1. To get rid of that plus 22, I'm going to do minus 22. Property of equality says I need to do it on both sides. I perform that computation. I end up with x plus 0 equals negative 33. And the additive identity says that adding 0 doesn't do anything, which gives me x equals negative 33. Once again, you can check that to verify that you're correct. Lastly, I did put another one with a fraction in there. These tend to be confusing for people, so I wanted to make sure you got some extra practice on it. Negative 7/9 times x equals 42. If I want to get rid of that negative 7/9 x, I'm going to want to multiply by the multiplicative inverse or the reciprocal. Notice that I just flip that fraction over and I get negative 9/7. Of course, I have to do it on both sides. I multiply those together, 63/63 of x equals 378 over 7. I make that negative. Once again, there are faster ways to multiply this fraction together, but for the sake of this video, it seemed less confusing just to do it longhand. And simplify. 1x equals negative 54. Multiplying by 1 does not do anything. And there is the check. What we're going to want to do today is we want to step this up and look at two-step equations. Now, in the last set of problems, we had our unknown, and we either multiplied or divided it by something, or we added or subtracted to it, or from it. In this case, we are doing both. Somebody has taken a number that's unknown, they've multiplied it by 5 first, and then they've added a 3 to it, and it equals negative 32. In order for us to find what value makes this statement true, I want to work backwards through that process in order to get the x by itself again. Once it's alone, it's very easy for me to tell what value is going to make it true. So I'm going to do that. Notice the property of equality says I can do whatever I want to an equation as long as I do it on both sides. That means I can add 10, I can multiply by 42, I can subtract 13, but some things are going to be more helpful or beneficial than other things are. Specifically, if I want to get rid of a times 5, my goal should be to turn it into a 1, because if it's a 1, I can use the multiplicative identity to get rid of it. If I have a plus 3, my goal should be to turn this to a plus 0, because if it's plus 0, I know that adding 0 doesn't do anything, and so I can use the additive identity to get rid of it. So I look at this plus 3 and I ask myself, what is it I could do to get rid of this? What would make it a 0? And then I remember that additive inverses always add up to 0. So the additive inverse of 3 is -3. Now you can argue about whether that's -3 or plus -3. Really makes no difference to me, but it is the additive inverse. Notice I wrote additive identity. That is a typo I'm going to need to go back and clean up a little bit later. Property of equality says I have to do it on both sides. So I perform some computation there, and I end up with that plus 0 computation. And of course, the identity property says we don't need the 0, which puts me here. Now I'm back to a single-step equation that is based on multiplication. I have this times 5. I don't want to have a times 5. I want to get rid of that and make it into a 1. The easiest way to make that into a 1 is to multiply it by its multiplicative inverse. What times 5 equals 1? 1/5. That's the multiplicative inverse. Once again, same typo. I have to go back and clean that up. So I multiply both sides by 1/5. Computation says 5 times 1/5 is 1, -35 times 1/5 is -7, and then this multiplicative identity says I don't need the times 1, which gives me a solution of x equals -7. Now, up here in the corner, I did go through and work out the check for you, but I'm not going to spend much time dealing with that right now. What I'd like to focus on real quick is this pattern right here. Property of equality, computation, and identity. Equality, computation, identity. You see that same pattern occur twice. In fact, when we're solving two-step equations, my goal is usually to try and get my equations to follow that same pattern because it's predictable, it occurs a lot, and it's something that I can always count on. If I can take large equations and turn them into two-step equations using this equality, computation, identity pattern, I can typically solve those without a whole lot of extra thought. It almost becomes automatic, leaving me to think about much more challenging things that might be occurring within the problem. Here's a second one. Now, I would encourage you to take a moment, pause the video, and try this on your own. We're going to walk through it the exact same way we did before. Notice someone has taken the x and they've multiplied it by a 7. They've also subtracted an 8. I want to work my way back through this problem to get that x by itself so I can know what number to plug in that would make it true. Now remember, the property of equality says I can add or subtract or multiply or divide whatever I want as long as I do it on both sides. Some things that I do are going to be more useful than others. In this case, since I already have a -8 or a -8, it is going to be very, very useful to make this into a +0. Using the additive inverse of +8 on both sides, notice again the additive identity, that is a typo. Notice that the property of equality says I do it on both sides. I perform some simple computation, and that gives me the +0 I was looking for. Identity property says we don't need the 0, so we get rid of it. Now it's a one-step equation. I have a number that's been multiplied by 7 to make it into a 63. If I can turn that 7 into a 1, I can get rid of it. Easiest way to do that is by using the multiplicative inverse. Once again, same typo. The multiplicative inverse of 7 is whatever multiplied by 7 equals 1. In this case, it's a 1/7. Now, you could argue that instead of multiplying by 1/7, you could divide by 7. That is the exact same thing, but in this case, I thought it would be easier to write it as a times 1/7 because you can see the multiplicative inverse very easily that way. Perform some computation. 1/7 times 7 is 1. 63 times 1/7 is 9. Identity property says we don't need the 1, and you have it by itself. Once again, I did go ahead and put the check in here for you. If you really want to look at that, you can pause the video. The important part for us to see here is this property of equality, computation, identity. Equality, computation, identity. That pattern is going to appear over and over again. And as I go through this series of videos, you're going to see me make reference to it quite a bit, and you're going to begin to see me work through this portion of the problem much, much more quickly, because I'm going to assume that you remember these pieces here. Now, whenever I do this, somebody always asks me, do we have to add the 8 first? Couldn't we just as easily divide by 7? Or how do we know that dividing by 7 would not be better? Well, I can tell you that you can actually divide both sides by 7 first if you want to. But if you do that, divide both sides by the 7, you're going to have to make sure you divide everything by 7. 7 divided by 7 would give you the 1x, but then you'd also have this minus 8 sevenths equals 55 sevenths. And I think you're going to find that x minus 8 sevenths equals 55 sevenths is much more complex to work with than if you had just done the 8 in the first place. Again, the property of equality says I can do whatever I want as long as I do it on both sides. However, some things are going to be more advantageous to you than others. Here's another one for you. X divided by -4 minus 13 equals -16. Once again, it is going to be my suggestion that you pause the video, try this on your own before watching it, because if I show you how to do it, you're going to get it right every time. It's much more beneficial to you to try it and see if you can do it on your own, and then if you can't, to go back and look for your errors, because that's going to reveal to you the tendencies you have, the errors that you tend to make. It's going to be much more instructive and helpful for you. I'm assuming now you've paused the video, you've already worked this out. Here's how this is going to go. I have to get rid of a divided by -4. Remember, that's the same as multiplying by -1/4. I have to get rid of a minus 13. The easiest way to get rid of a minus 13 is to turn it into a 0 by using its additive inverse, adding 13 to both sides. Notice once again, same typo. We underline that. -13 plus 13 is 0. -16 plus 13 is -3. There's your computation. Property of equality, computation. We don't need the plus 0, so we use the identity property. That's the additive identity. Since this is times -1/4 or divided by -4, the easiest way to get rid of that is to turn it into a 1. Oh, I did go ahead and show you that I'm writing it as a fraction instead of division. The easiest way to get rid of that and turn it into a 1 is to use the multiplicative inverse, not identity, same typo, which is -4/1. We multiply that together, you get 1x equals 12. Identity property says we don't need the 1. And of course I have the check for you, which is the check from the last problem. Wow, this is a terrible video, isn't it? And through the magical power of editing, you can see that the multiplicative inverse and additive inverse problems have been corrected, and you can see that the check is now as it should be. It's interesting to you, that didn't seem like very long, did it? But it took a few minutes on my end, and we just splice that together in post-production. So one more two-step equation. I'll invite you to pause the video, try this one more time on yourself. By yourself before watching me do it. I'm going to go ahead and go. I look at this, and the first thing that I notice is that this is a 3/5 x minus 4 equals -31. I'm going to do something a little unfair here because I hadn't mentioned it before. I'm going to go ahead and use something called the symmetric property. The symmetric property teaches us that if you have two things that are equal to one another, like this -31 is equal to this 3/5 x minus 4. If two things are equal to one another, then they're equal to one another whether or not you put them on a different side of the equation. So if I say to you 4/4 is equal to $1, that's the same as saying $1 is equal to 4/4. It doesn't matter which side you write it on, they have the exact same value. So I'm going to go ahead and switch mine using that symmetric property. A lot of people don't like to have their x's on the right side of the equation. You can and probably did solve it with your x on the right hand, but you may find that having it on the left is a little less unfamiliar, a little less uncomfortable for you. So I'm going to go ahead and move it to the other side. It's called the symmetric property, a fun little trick. I'm then going to use my property of equality to add 4 to both sides. Now, up until now, I've been writing them underneath the -4, but there is a second way to do it, which is over here on the right of the numbers, and this is fine as well. I believe in the first video we talked about that as being an alternate way to do that. I went ahead and did it this way because I wanted you to see that we are using the property of equality in that particular step. I perform a little bit of computation. The additive identity says I don't need the 0. I'm then going to go through and use the multiplicative inverse of the 3/5 in order to change it into a 1. Notice I used the property of equality there because I did it on both sides. Becomes the 1. I did do the multiplication, -31 times 5 over 3. That's just computation. I don't need the times 1 because of the multiplicative identity. Hopefully those examples have been enough to give you a pretty good idea of how to solve two-step equations. Solving two-step equations is really the foundation for all our work with larger equations. Most of the time when I'm working with those larger equations, I have this goal of turning it into a two-step equation so that I can get to this point where it's automatic. Notice here, equality, computation, identity, equality, computation, identity. That's going to come up over and over again. So, congratulations. And one last note before we go. Ann Landers once said, opportunities are usually disguised as hard work, so most people don't recognize them. I know some of what we've talked about might seem a little bit challenging, but trust me, it is all about putting in the time and effort. Repetition makes a huge difference. You can do this. If what you've seen here has been helpful to you, please feel free to like and subscribe. And I've been told by my students that I need to ask you to turn on your notifications as well. Also, please leave a comment in the comments section so that we can hear your thoughts on the matter. If you have some suggestions, you can put those there as well. Thanks a lot. Have a great day. Take care.